So in creating our L1, X1, we grew an idea of a protocol design based on first principles, but we were agnostic in terms of which virtual machine to go with. Actually, this is not the first slide. If you could go back, please, to the start. Thank you. Yeah, so in creating our L1, we were growing an idea of a protocol design based on first principles, but we were agnostic in terms of which virtual machine to go with. So we forked a bunch of chains and we crashed a lot of stuff. And I will share some insights based on our experiments that ultimately led us to the Solana virtual machine. But let's start with some very basic concepts to get everybody on the same page. So when we're creating scalable infrastructure, we assume that oh, is this the clipper? Good. There we go. All right. When creating scalable infrastructure, we assume that demand is infinite and capacity is the constraint. So the challenge in creating protocol design is to optimize both for scalability and performance on one hand, but also making sure that decentralization grows over time and doing this in a way that is making sure that we are censorship resistant, right? So we don't have a few actors that can collude, and in a way that is secure with a finite capacity. And capacity is limited through space and time. Sequential block production involves using a container known as a block, which is limited with a specific space and also restricted to be confirmed within a specific time. So protocol designers have chosen to translate these block limitations differently. Bitcoin doesn't have a gas or compute system because it doesn't support complex variable cost transaction. Bitcoin's main constraint is block size, which limits throughput, not computation. In contrast, Ethereum and Solana limits computation per transaction to prevent spam and maintain network performance. So essentially, there's a bid and auction with a limit in space and time, and transactions are competing to secure a spot in the next block. So the question is, how much are you willing to pay in this auction for block space? So if your bid is too low, you don't get in. So you have to up your bid. And it's this upping of bid that not only can cause your chains transactions to spike, but also ultimately crash, which I will give some examples of today. So the question is, how can we solve for congestion and scale? And what happens when we push this blockchain to the limit? So what we did is that we took a purely empirical approach into stress testing major L1s and L2s to uncover what their design limitations are under load. So if we begin with Bitcoin, we basically proved that it's unable to scale. We launched a BRC20 token called BNPX, and it cost, due to very high demand, an unprecedented spike in transaction fees, over 600 sats per virtual byte, which you can see here. So it caused a very big disruption to the Bitcoin network, which resulted in that Bitcoin became completely unusable. It had cascading effects. Binance had net negative outflows of $5 billion. And the question is, if Bitcoin can't even handle one token launch, then how will it accommodate global demand? We also can draw the conclusion that if you're malicious, you can basically make Bitcoin completely unusable with just a few $1 million, which is what we did. But even though we empirically prove this now, it's not a new insight. Hal Finney, 15 years ago, even promoted a secondary level or modularity for Bitcoin. And how Bitcoin will reach its intended use case as a peer-to-peer currency is still very much unknown. So Bitcoin maximalism has never made any sense whatsoever. Now to Ethereum, we have computational capabilities with smart contracts, and our partial intent here was to consume as much block space as possible. So we created this protocol called ZEM protocol, which is a gas arbitrage protocol, and the arbitrage is between the gas that a user pays in this immutable protocol today versus at a future time relative to the token price at that future time. So we then baked this into another protocol called Zen Torrent protocol, which allowed bulk minting of this gas arbitrage, only limited by the 30 million gas limit. So we deployed this on 13 different EVM chains, and Zen is the most used application in the entire EVM ecosystem in terms of transaction volume, but also block space occupancy. So we have a lot of good data to draw conclusions from. If we look at storage consumption, 4% of the entire state of Ethereum is Zen. This number is there we go. This number is 70% on base, so 70% of the entire state of base is Zen. Evmos really struggled with the Zen contracts. 96% of the entire state of Evmos is Zen, and they reported that it severely slowed down processes related to reading and writing, analyzing on-chain data. It significantly increased costs for infrastructure providers, and this includes validator, archival nodes, indexer services, and RPC nodes. And it severely impacted the overall functionality, so much so that it led to the censorship of the Zen contracts, and these are immutable contracts. The same thing happened to Dodge Chain with the Zen contracts as well. So let's take this into the context of pricing block space. Now, EIP 1559 was a great success, you have to say, for Ethereum because it introduced this dynamic burning mechanism for the base fee. So now a user pays a fair price based on the computational resources used directly tied to overall block space demand. And Zen is a perfect example of this dynamic because it actively contributed to making ETH deflationary. In fact, as you can see here, when Zen launched, that was a time when ETH became deflationary due to the fact that it directly involves with gas fees. So thanks to EIP 1559, Ethereum was able to capture this high transaction volume caused by Zen, but other EVMs struggled, as we can see with Evmos. And if we look at this forum post from Moonbeam, they hit the nail in the head when they say that the fundamental problem is that the dynamic fee model of our chain doesn't adapt well to this spamming. So, so we're going to look at how Solana handles price auctions, but first we need to understand how Solana is different. On Ethereum, validators are executing transactions using a single thread. So we have a global state for execution, which effectively means that every transaction affects everything else, which is part of the reason why Ethereum is so expensive to use, which is why we have L2s in the first place. Solana, we have parallelization, which means that we can use multiple threads. So we get faster transaction processing with local fee markets. So every thread is its local state, which effectively means that a hot NFT mint won't affect the whole chain. So to simulate or to stress test parallelization and to simulate a highly congested environment, we created this proof of work mining script called Solsen, which separated mining from minting, and this allowed us to target all threads without being limited to one thread by the scheduler. So it's kind of like Ori, if you know what that is, but it's completely different in the sense that primarily you're not mining with your own hardware. We simply sent a transaction for with an instruction to the validators of Solana to mine for us. And effectively, we were able to monopolize block space at a minimal cost. And we were able to occupy around 30% of Solana's entire network capacity continuously during 6 months. With only 43 transactions, we were able to consume entire blocks. And we did this by targeting all threads, but also setting very high compute unit budget per transaction. So Solana limits 1.2 million per transaction. They have a total budget of 48 million. We set it to 1.1 to have some margin. And effectively, that led to this result. Now, to be fair, it would be much harder to do this today because ANSA has done a very good job in improving the scheduler. But another reason why we were able to do this is because Solana has a fixed base fee of 5,000 lamparts per signature. So I'm going to double click a little bit more on pricing. Back to Ethereum, EIP 1559 has had, even though it was great for the chain, it has had little effect for the users because you still pay high transaction fees. And this is due to the sequential transaction processing, a global fee market state, and long block times, which cause these price auctions to escalate. So it's still very expensive to use Ethereum. And this is despite that Ethereum has lost a lot of traffic, as we can see on the gray charts here. Back to Solana, we have this parallel transaction processing, which enables these local fee markets, which you now all know how that works. So even though Ethereum has a more deflationary pricing model, Solana is still cheaper to use. And I think this chart is very beautiful because we have high average fees, which speaks to the point that's of security for the chain in the sense that validators are getting paid. But we also have low median fees, which allows for low accessibility to the chain. But the question is, who benefits from this low accessibility? Addresses that send thousands of transactions per day are likely to be bots. And as we can see, the revert rate here increases with these spam bots. So these transactions exploit Solana's low accessibility. They're enabled by the low fixed base fee model by spamming the network in hopes of occasionally succeeding. And this strategy remains economically viable even with a low success rate. So as the fixed base fee enables these attempts to be executed at scale. And here we can see the high share of reverted transactions that indicate this economically viable underpricing. So we have unnecessary spam on the network. These MEV bots compete for arbitrage opportunities. This spam is mostly MEV transaction, underpriced MEV transactions in the transaction pipeline. And that includes front running, sandwich attacks, back running, and censorship attacks. So out of 1,200 non-vote TPS, roughly, this is a gross estimation, but roughly 20% are non-bot, whereas 80% are bots. And it sort of creates this player versus player situation where 80% are capitalizing on the rest of the 20%, which is, of course, not ideal. Back to Solsen, our proof of work mining experiment, it acted as a spam filter for these underpriced MEV transactions. And this occurred because each Solsen transaction consumed this very high amount of compute units per transaction, and our miners were allowed not charging per CU for the fixed base fee. So effectively, what we were able to do is displace this spam by increasing the competition in the network resources. So to compare these pricing models, Ethereum, we have a global fee market. We have a maximum fee, which is a combination of the dynamic base fee plus priority fee. On Solana, we have a fixed base fee plus local fee market based on priority fee per thread. And we think that a combination of these two pricing models would be optimal because now we can have a dynamic base fee based on the transaction compute unit consumption and thread congestion. So congestion reflective dynamic base fees. And then we have local fee markets based on priority fee per thread. And this way we can ensure fair pricing of the block space. We reduce spam and we have a very high deflation at the same time. But let's talk about how this relates into consensus, because Ethereum's bottleneck is not execution, it's consensus. So block times are 12 seconds to accommodate for the slowest validator in the network. And this delay creates a mempool buildup in global fee auctions who are driving up these gas prices. So users still pay a very high GUI to skip the line, but it's not due to throughput, it's because consensus is slow. So why is Ethereum slow? Well, we have a low hardware spec on Ethereum, and that increases decentralization. It's good because it allows the low-powered nodes to participate in consensus. So block times have to be slow for that reason. But we have to understand that this is at the expense of performance. We restrict parallel processing and high throughput. We are therefore forced to scale with a modular design. And to achieve low cost and high speed, users go to central sequencing L2s, which we can see in the dominance chart here, the L2 dominance chart, or even centralized exchanges. But this is at the expense of, we have compromised decentralization, we lose the atomic composability, we increase the risk and fragmentation, which then have to be patchworked with fraud proofs and stuff like that. So in essence, we have an underperformant L1, which now we are relying with an L2, and this creates this unnecessary filter between the user and decentralization, between the user and real self-custody. And not only that, scaling with L2s also means that these cannibalistic L2s are capturing all the users and fees and thus taking all the revenue. But we also have to understand that execution and competition in priority fees are the prime drivers of revenue. So the L1 doesn't capture this value or MEV at all. The L2 generates their own revenue with their own central sequencing, and that's the reason why it makes it parasitic to the L1, creating these competing environments. And over time, Ethereum risks becoming just a replaceable DA layer with little or no revenue at all to ensure its sustainability, especially as its primary source of revenue, the cost of storage continues to approach zero. So in effect, Ethereum is a $315 billion interchangeable hosting provider for security, lacking a sustainable revenue model while urging the world to move from one centralized system to another in the name of decentralization. Vitalik Buterin has not approved of this mission statement, but it's just a proposal. Maybe I won't get invited back to Protocol Berg after this, but it's totally worth it. So I want to finish by talking about block building accessibility and the importance of validators, because blockchains were created to create censorship resistance. We're eliminating middlemen. We're enabling Alice to transact freely to Bob. Validators, they're the core participants in a blockchain. They process, execute transactions, they build blocks, they reach consensus. And a larger validator set reduces the likelihood of a few actors colluding to censor protocol or prevent individuals from transacting on chain. Now, this is just first principles thinking. I think most people would agree on this fully. Validators are important, and the reason we want decentralization, in my opinion, is primarily so we can offer the world censorship resistance, so we're not dependent on a few actors to collude. But how does it actually look like today for these networks? If we begin with Bitcoin, the true innovation is that we could go from one person, one vote to one CPU, one vote. But SHA-256 as a cryptographic hashing algorithm allowed for the specialization of hardware. So we used to mine with CPU, then GPU, then FGPA for a short while, and then ASICs. And now mining is heavily concentrated among a few dominant pools who control a majority of Bitcoin's hash rate at times. And this is also why Bitcoin's Nakamoto coefficient is so incredibly low. And this creates a lot of problem, because if this centralization goes on over time, there are centralizing forces that need to be counteracted, that are, for example, regulatory frameworks that favor large-scale miners over smaller participants, or access to mining hardware energy becomes increasingly exclusive. If you look at Ethereum and we begin with the block building accessibility, PBS allowed for centralization of block builders. So we have Beaverbuild and Titan, who control 80% of the block building market share. And this creates a monopoly over time, and a monopoly means no choice. It's an oligopoly, but it becomes a monopoly. at 1.5 out of 6 block builders even censored tornado cache, and it's not about tornado cache in itself, but it's about the fact that censorship can happen, and we're down to a few actors who actively can censor. And this is also a reason why Ethereum has a low Nakamoto coefficient. If we look at the proposing side, we have 1 million block proposer, so Ethereum is decentralized, right? Well, Lido has 30% of these. You can't do native staking. You have high barriers for validator with 32 ETH, and you also have trust-based delegation. So we need to understand that, well, first of all, the question is, why do we have a low hardware spec to begin with if we have these high barriers? Second of all, we have to understand that consensus participation must be evaluated based on both hardware, both technical and financial barriers in terms of accessibility, because both the technical and financial barrier represent significant barriers for individual validators. And now Solana, when it comes to block building accessibility, I think Solana gets a lot of FUD for the high hardware spec, but in my opinion, you need this in order to be able to accommodate low costs and high speed. You need these high throughput servers, because otherwise you're gonna be forced to scale with a modular design. But also the server cost is only a small portion if you look at the financial side of the total operational costs for a validator. It's only a few percent. Over 90% on Solana today is that you have to pay for these vote costs. So, and out of the vote cost, 50% gets burned, 50% gets to the block rewards bucket. And since Solana is solely based on stake weight, it means that only a few validators can tap in to these vote costs. And effectively, what's been happening is that there's a redistribution of wealth going from smaller validators to bigger validators. And it's part of the reason why out of 1,400 Solana validators, only 400 are profitable or self-sustaining. And this is also part of the reason why Solana has a very low Nakamoto coefficient, even though it's bigger than Ethereum and Bitcoin combined. So you could make the case that Solana is more decentralized. But also to mention, some validators, they did censor source and transaction, and understandably so, because they would rather take 1,000, 5,000 LAMP ports per signature transactions from spam bots instead of one transaction from the Solsan, who just occupied a big part of the block space. So you can see that the Moloch effect is very strong here. And I think there's been like 10 million pump.fun tokens launched. I don't think anybody cared about censorship in that aspect, but if you want to handle a nation state's medical records on chain or something like that, these censorship guarantees that you can't really provide become increasingly more important. So my point is both Bitcoin, Ethereum, and Solana has very high barriers to participate in the block production. So for X1, what we've been working very hard with is to solve the shortcomings of the previous chains. So first of all, we have very low barriers to become validator. Validators don't have to pay to participate in consensus. We don't have vote costs. You only pay for your own hardware. There's no high staking requirements. And to ensure decentralization and censorship resistance, we create this anti-collusion protocol, which essentially means that we distribute the block rewards with the whole validator set with a combination of stake weights, randomness, and performance and reputation in the network. So in this way, we can ensure strong censorship resistance and even be able to provide censorship guarantees. And conclusions based on first principles. Okay. All right. Our conclusions is that we think that you should still continue to develop a monolithic chain in order to provide this atomic composability. So that's what we are doing. We're having low barriers to maximize the validator sets, but we're also decentralizing block production eligibility with randomness and VRF, so we can have a high Nakamoto coefficient and censorship resistance. We have chosen the SVM engine based on our empirical research show that it had the best performance, and we're doing some modifications, of course, to the protocol design, but we're keeping the virtual machine engine, and we're very much Solana aligned. We have high respect for Anatoly's disruptive vision, ANZA, in terms of their ability to create a very good virtual machine, and we are very happy to continue to help them in that journey and making the SVM better by finding bugs and stuff like that. And therefore, we have a multi-threaded execution. We have high throughput, low latency, and we have our pricing model, dynamic base fees, local fee markets, fair block-based pricing, less spam, and high deflation. So please join our validator network. We just crossed 400 validators, so very happy for that. Thank you, everybody, for listening. And yeah, if you have any questions, I'm going to be here after. So thank you.
Thank you so much, Axel.